Hello, welcome to this short video on how to find oxidation states. Oxidation states, what does that mean? Oxidation states are a measure of control an atom has over electrons in a compound. It's written kind of like a charge, but it's not actually a charge. It's really just giving us more information about which atoms are more electronegative or less electronegative within a single compound. All right, so in order to find oxidation states, I'm going to start with this periodic table here, and hopefully this is a bit of a review. We know from 10th grade chemistry that the number of valence electrons for main group elements matches up to the group number. So everyone in group 1 has 1 valence electron. Everyone in group 2 has 2 valence electrons. Group 13, 3 valence electrons. Group 14, 4 valence electrons, 5, 6, 7, 8, except for helium, who only has 2 electrons total. So those 2 electrons would be its valence. As a reminder, valence just means electrons in outermost or highest energy level, the energy level furthest from the nucleus. All right, we can also use this to predict the charge of an ion that would form for any of these elements. That's going to be the same as the oxidation state for main group elements. What do I mean by that? Well, anyone in group 1 who's going to form an ion, they have 1 valence electron. If they need to get to a full shell, which is easier, losing that 1 valence electron so that the shell underneath, which was already full, would become the valence, or gaining 7 valence electrons in order to get to a full shell of 8. Remember, we're just looking at main group elements here, so only s orbitals and p orbitals are relevant. So I am referring to valence shells of 8 and not worrying about the d orbitals or f orbitals for now. All right, so back to group 1, which is easier, losing 1 valence electron or gaining 7. Obviously, losing 1, and so everyone in group 1 should form a charge of +1. If I lose 1 valence electron, I have a charge of +1. Group 2, very similar. Group 3, very similar. Let's take a look at group 7. Group 7 elements tend to, or 17, excuse me, tend to gain 1 valence electron. If I gain an electron to go from 7 valence electrons to 8 valence electrons, my charge is -1, -2, -3, 4, of course, +4, or -4, depending on what it's bonding with. Obviously, noble gases tend not to form compounds. All right, so these are charges that ions tend to form. They also correspond with oxidation states. Let's see an example of what this would actually look like in a compound. So, oxygen. I always start, when I'm finding oxidation states, I always start with the most electronegative element in the compound. So oxygen, most electronegative, oxygen, -2, group 6, going to have a charge of -2, or would have a charge in an ion of -2. Remember, oxidation states are not actual charges, they are oxidation states, but they get the same number. All right, so 6 oxygen atoms, each with an oxidation state of -2. That gives me a total of -12. Hydrogen. Hydrogen tend to be +1, both for the ions that they would form in oxidation state. Cool. That would give me a charge of +12. This leaves me with a carbon oxidation state of 0. Notice carbon is often not 0. Carbon can be +4 or -4, but the way that I figured this out, I had to start with the most electronegative element, which was hydrogen. I then moved on to carbon, and excuse me, I started with the most electronegative element, which was oxygen. I then moved on to hydrogen, and then based on the other oxidation states, I figured out carbon. All right, This is elemental oxygen. Oxygen is a diatomic element. It fits into our Hofbrinkel rule. Oxygen is diatomic, meaning this is the elemental state. Elemental states always get oxidation number of 0. What about here in CO2? Well, oxygen, I'm starting with the more electronegative element, which is oxygen, gets an oxidation state of -2. So 2 atoms of oxygen, each with an oxidation state of -2, would give me -4 in total. And the sum of the oxidation states need to equal the sum of the compound or ion I have. Here, in this case, I have CO2, which is a compound, which is neutral. So all of the oxidation states need to sum up to be neutral. So if 2 oxygen atoms each have a charge of -2, that leaves carbon, in this case, with +4. Notice the oxidation state changed from the beginning to the end. That's kind of cool. What about water? Again, I start with the more electronegative element, -2. And so this is -2 in total. That leaves hydrogen to be +1 because 2 plus 1s would be +2.